So we saw how to represent signals in MATLAB, so how do we calculate signal properties? That's the next topic we'd like to discuss. So we'd like to be able to find power and energy for signals and the periods of periodic signals. So for discrete time signals, the energy of a signal is pretty easy to calculate because discrete time signals, everything is a little bit easier. They're already arrays in MATLAB. So let me define a function which is windowed. It's a cosine, just windowed between 0 and 7. So again, I can use these Hadamard products, this dot star, to limit the signal between 0 and 7. And I can plot the signal, and then either I can calculate the sum. This sum is going to be summation over n, x of n squared. That's what this summation of x dot star x does, because the dot star multiplies element-wise x by itself. If I wanted to have a complex signal, really I should do abs of x, squared, because that would give me the magnitude squared of a complex signal. So for periodic signals, we can calculate the power in one period only. Remember, we have this formula. We can say it's 1 over n0 summation n equals 1 to n0 x of n magnitude x of n squared. So here we have this sum of magnitude of x of n squared, and we divide by 5. The period of this signal is 5, this cosine 0.4 pi n. I'm plotting it over one period, from 0 to 4 in this case, and then I can just compute the power that way. So that's if I know I already know the period of the signal. So what about continuous time? So in continuous time, you have to remember that we're actually approximating the continuous time signal by a discrete time signal. So here I'm going to set the sampling rate to be 10 to the 4. And then I'm going to look at, again, my time axis is divided up into intervals of length. This is our little delta t, which is equal to 1 over fs. And here I'm going to plot some signal which is like a polynomial, looks like a cubic function of t, look between -2 and 4. Right, so this is that's what this third line does. And again, what I can do is I can, here's a different way of computing x dot star x. I can take x element-wise square, right, and then I can take the sum of x element-wise square. So this is going to be, this is a discrete approximation. And what we have to think about is what does one, so we're basically saying we're looking at an interval of the length here, delta t, and we're saying, oh, this is the value at delta t. And so the total area under the curve is delta t times x of t. X of x of t, right, at this point t. So we need to sum up the total area under the curve, but then we have this multiplied by delta t factor, so we have to account for that by essentially multiplying by delta t, which is 1 over fs, right? So we get that in the last line. Okay, so what about power for CT signals? So here it's a bit challenging. Even for periodic signals, the period might not be an integer multiple of 1 over fs. For example, the period could be a irrational number, so we can never really get it as 1 over fs. So we can try to empirically calculate the limit, like just simulate a gigantic length of our signal x, and then square it and sum it up, and then divide by 1 over 2t, and then of course, we have to also factor in the sampling frequency, fs, or sort of the delta t in the previous page. And of course, this is going to be computationally a bit hairy because how long do we have to simulate it? And, when do we think we reach the limit? And so this is a little messy. If our signal is periodic, we could first try to estimate the period of the signal and then just compute, the energy over one period. So this raises some interesting questions. So if I want to do the numerical limit version, I can say here, take my sampling rate from 1 million, 10 to the 6, so 1 million samples per second. And then I can look at, say, minus 1,000 seconds to 1,000 seconds. So that's 2 billion samples, right? So that's 2 billion numbers that I've decided to compute. And then I can square 2 billion numbers and sum them up and divide by fs. And then here I'm dividing by t, right? So this is the total energy here. So this is the energy. And this is the time. And I could try to compute my power that way. This is the power. This is computationally intensive. You could try it out. It may run. It may not perceptibly seem super slow, but you could just make this 10,000 to minus 10,000 to 10,000, and then you'll start getting to see how it's slow. And the other main problem is you don't really know whether you've reached the limit at all. So let's look at option 2. First, trying to find a period. If it is a periodic signal, try to find the period of it. So note that if you delay a periodic signal, so suppose I have a periodic signal that looks like this, right? And here's t0. Now suppose I delay this by t0. Remember, this is going on infinitely long over here. If I delay it by t0, I get something that looks exactly the same. Right, so this is x of t minus t0, right? So this sliding process can be represented by something called the autocorrelation function, which is defined as basically this integral from over the function. So we're going to take x of t, and this is a delayed copy of x of t here. And here I'm taking this complex conjugate to handle complex signals, but let's think about real signals for now, in which case it's just x of t minus tau. Now, a problem here is I don't know t0, the period of the signal. So instead, we're just going to take a large enough segment of time. So we take t, like t is big, and then we just compute this function, which is just kind of the basically like the autocorrelation function without the normalization factor. We just compute this delayed version of itself. And this is a function of tau. This is a function of the delay. Or sometimes it's called the lag. So there's a peak at tau equals 0 because they line up perfectly, and their next largest peak should be at plus minus t0. So let's try and see what this looks like. So you can use the xcore function in MATLAB. It's cross correlation. You can generate your signal, say it's from minus 20 to 20, and then you can compute the correlation, which will return to you both the autocorrelation and the lags, and then if I multiply by my delta t, I can get an approximation of the signal. So you can see here, I take my signal and I'm going to get these little peaks here, 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 and so each one of these little peaks, because I'm only simulating it from minus 20 to 20, these peaks are decaying because I'm getting less and less overlap. But basically we want to find second highest peak. And here we know that the omega is equal to 4, right? Which means that the period is going to be 2 pi over 4 or pi over 2, which is not rational. So we're not going to be able to capture it perfectly with a integer sampling rate, fs. So we want to find the second largest peak. So if we want to find the second largest peak, we can use this function findPeaks, which is also in MATLAB. So MATLAB makes things easier because it sort of builds in a lot of the stuff that we learn how to do in the class. But let's just take it as given. We can find this use this findPeaks function. We can sort the peaks in descending order and then choose the second one. So choose the second, right? The second highest. I'm sorting it in descending order, and then I can compute the approximation to t0 as the absolute value of the second peak. Why do I need this absolute value? Because it may choose minus t0 as the second highest. So the last part you want to do is calculate the power. So now we just segment out one segment from 0 to t0 of the signal, calculate the square of the signal, calculate its total energy. So again, remember this is energy. Divide by the time, and we get the power of the signal. And you should compare these two. Try and run these on MATLAB yourself and see what you get from doing your long integral, and see if you get the same answer that you would get by doing it this way. So trying it yourself, you should basically look at some of the signals we saw before. Try it for complex valued signals. I think that's pretty instructive. And then look at the documentation for the X-core, the cross-correlation function, to see how it works also for complex signals. That'll give you some insight into how all of these things work together.